This playlist is about reservations in two-way slabs by means of yield lines. This video will deal with case 2, and case 2 is the following. Consider a rectangular slab continuously supported on all sides with a size A and B, where B is between A and 2A. So this condition is needed to have a two-way slab. In this slab, we have drawn the original yield lines. That means the yield lines when the ultimate load is on the slab. And then we have now at case 2 reservations in the slab, which is a square hole, a square reservation in the corner of the slab with a dimension d1. So within the reservation, this yield line is not there. So the conditions for this case 2 are d1 is equal to d2. The top left corner means that d4 and d3 is 0. And we are cutting only one yield line, means that d1 must be between 0 and a over 2. Now, take into consideration all those limitations, then we have a reservation like, for instance, there in the corner. It can be bigger, can be more bigger, and you end up there. So it's between this hole and this hole. For case 2 elements, we can now calculate the bearing capacity of the slab. Again, we start to divide the whole slab into triangles and rectangles, but we can do it a little bit more simple, or simplify the method. What we do is we take the work done by the external force of the slab without reservation, and we subtract the reservation, the work done by the external forces on the reservation. So what we obtain then is you have in the beginning the triangles, which is A times A over 2 times 1/3, because it's all about triangles. We take this side, ignoring the whole. That's why there is 2. Now we take the rectangulars, which is A times B minus A times A over 2. So you get this, and then we subtract the whole. And then we have to look at the mean deflection of that hole. Then we know that when this is delta, this line is delta, so that point is delta. So you see that for d1 there, the deflection is v1 over a times 2. So now we have the reversal work done by the external forces. We now look at the internal bending moments, their virtual work done. And there it's quite simple. We do the same thing. We take the work done for the whole slab without a hole, and we subtract the yield line here, this one, which is corrected to the rotation axis of there and the rotation axis of there. So we have 2 times E1, the length, multiplied by the angle, which is the angle, not the deflection itself, but the angle, which is the A over 2, delta divided by A over 2, sorry. So then we can simplify the equation, and when E is equal to D, M must be equal to this pretty formula. So for reservation in the slab type 2, case 2, this is the maximum bending moment in the slab. Let's now have an example. You have a slab 5 by 8 with a reservation of 1 by 1. The depth of the slab is 15 centimeters, concrete cover 25 millimeters, the floor finish is 2 kilonewton per square meter, and the mobile load is, for instance, 5 kilonewton per square meter. What is the needed reinforcement in this slab? Well, the load in ULS, it's 1.35 times the permanent load plus 1.5 times the mobile load. This gives you 15.26 kilonewton per square meter. Now we can use the formula that we have developed in the previous slides. We fill in the 5 and the 8 meters and the size of the reservation 1 meter, and we obtain a maximum bending moment of 25 kilonewton meter per meter. The lever arm in the X direction is then the total depth of the slab minus concrete cover minus the point of gravity of the tension reinforcement. So we assume the diameter is 10, all diameters are equal. So just remember that. So when this is not the case at the end of the exercise, we have to redo the calculation. The lever arm in the Y direction, which is in the second layer of reinforcement, we obtain 110 millimeters. So the mean lever arm is 115 millimeters. So the needed reinforcement, as the same as in X and Y direction, is 1.1 times the bending moment divided by the lever arm and the yield strength of the steel, which gives you 611 square millimeters per meter, or diameter 10, 8 per meter will be okay. Second example where you can use the formulas is you have an existing slab. It's there. So you know that it's reinforced in the two directions with the same reinforcement. And it is asked, is it okay to make a reservation in this slab on the left top corner with a size of 0.7 by 0.7 meter? Can we do that? You don't know what is the original bearing capacity. The only assumption that you make is that the reinforcement is okay to take up the original bearing capacity. The maximum bending moment without the hole, the original one, is because you don't know Q, which is the bearing capacity, you divide it by Q. So you have a parameter M0 divided by Q. That you can calculate, and you have 1.04 meter per meter. The maximum bending moment with the hole, and the hole is there, we use the formulas that we developed in the previous slides. You divide by Q again, and you have 1.11. So now it's easy. You just divide one by the other, and you see that you have 6% loss in bearing capacity. So by making a hole 0.7 times 0.7 in the left top corner, you lose over the whole slab a bearing capacity of 6%. Now, bearing capacity is defined at hundredths times maximum bending moment without the hole divided by the maximum bending moment with the hole. So in formula, it becomes like that. And now we will make all elements without dimensions. So D1 equals alpha 1 times A, and B is alpha times A. We know that in case two type of holes, we have certain restrictions. And then we can rewrite the formula of the previous slides with those assumptions. And you arrive at this equation. Now, on the y-axis, we write these equations. For instance, for alpha, which is the ratio of the length of the slab divided by the width of the slab. So when it is a square slab, that's the red curve. This is a square slab. Then you have the blue one with a ratio of 1.5, this one with a ratio of 2, and this is 100% bearing capacity. Now what you see is that from this graph, on the x-axis, there is the dimension of the reservation in the slab. Dimension of the reservations times the smallest dimension of the slab. So for instance, in 0.4, you have 0.4 times A, which is the dimension of the hole in the slab. Now what we see there is that everything is below 100%. So it means that if you, in the left top corner, make a rectangular hole in a slab, it will always reduce your bearing capacity of the slab, which is interesting to know. Even if you have a small hole, it will reduce your bearing capacity. The maximum loss that you will have is for a square slab. And then you will see that you can, at the maximum, you lose 10% of the bearing capacity, which is that point there. Now we can, with alpha equals to 1.5, this means this is 1.5, this dimension, which is the blue dotted line, and alpha 1 is 1/6. So 1/6 is somewhere here, the blue dotted line, and you will arrive at 93.8. That's the blue dotted line. You have at 2/6 or 1/3, you will, this is this hole, then you have 90.5, which is somewhere here. And when you have alpha 1 is 0.5, which is at this side, you will end up with 93, which is this point there. Now, the basic conclusion is that a square hole smaller than half of the smallest side of a rectangular concrete slab leads to a loss of bearing capacity of a maximum of 10%. There is always a loss of bearing capacity with a reservation of that type from there until there.